I'm going to repeat a lot of the previous lecture today in a different way. I think that finite state machines is an important enough topic that I need to cover it twice with different slides and different examples each time. So this is going to be a little bit of a repeat there. And let me just kind of jump in here and talk about So this is a different approach, same topic, same thing there. I'm going to go a little bit more detail today than I did the other day on finite state machines, because last time I kind of introduced the subject, and I want to kind of get into it in a little bit more detail here. Right there. Okay. Again, these slides I'm using for other purposes. These are actually ones you can tell that we're going to look at not in assembler but in C. So I changed my mind. I'm going to be moving a lot of this course over towards C. So when I go through my example on finite state machines at the end of the hour, it's going to be looking more at how we would do that in C. I'm going to not finish the example because I'm going to have you start this as your lab starting tomorrow. That's there. So keep in mind that tomorrow's lab we're going to be setting up that there. I have hopefully tomorrow is what, Wednesday, right? Your lab is 8 o'clock tomorrow downstairs. So we may be writing it. I may be giving you a lab as you're doing it and typing up the specs as we're going through it. But we're going to look at finite state machines, and we're going to be doing a washing machine is what I'm doing for this particular example here. That's there. And it's an integral part of software programming. It's the guy here is finite state machines is it's a design tool. That's here. It's not a programming language or anything else. It's a tool that we use to write our software in this particular case. It can be used to write software in assembly language. It can be used to write software in C, like we're going to be doing. It can be used to design hardware. So, for example, you can look at finite state machines and do that in terms of state, next state, in terms of designing counters. Out there, you can use it in design software, design languages such as VHDL and Verilog for designing hardware. It's a design technique, and it lends itself very, very well to microcontroller and microprocessor applications. Right there. It's not limited to firmware. What we're doing in this class is actually what I call firmware, and firmware is the software that we program into the IC or the chip that it's hard fast into the that there. You don't change it. Software refers to something that's on a floppy disk that you can change, that there. It's code that you load in and out of there. So we're going to look at, again, I lied here. I stole these slides from a previous class. So what is a finite state machine? Idea that there's a finite number of states that a system can be in. A state has to be in a particular system, right there. So when we look at our example of a washing machine, everybody on this side of the room here knows when I talk about a washing machine. The ladies understand washing machines well. They know how to use them, right? Everybody over here has probably seen one, right? And you watched your mother use it, right? And maybe your sisters, but you probably never used one, right? That's it. Well, unfortunately, Americans, we force our kids to use washing machines. Actually, my son, when he was 13, I refused to wash clothes for him anymore. He had to do his own laundry from then on out. That's there. But a washing machine has a number of states that it operates in. And I'm just going to kind of give them verbally, we'll write them down later on. But when we first turn on the washing machine and we plug it in, it sits there and looks at us like it does nothing, right? You walk up to a washing machine, it's turned on, you see the power light on, and it's doing absolutely nothing. It's in what I call the idle mode. It's waiting for something to happen. Right there. You put your dirty clothes into the washing machine. You know, the guys here, you wait for your sisters or your mother to put your dirty clothes in the washing machine. Ladies, you put dirty clothes in the washing machine, right? Up there. And what do you do when all the clothes are in the washing machine? What do? You hit the start button, right? There's a little button there that says start. Now before that, you jiggle some switches and tell it what type of clothes it is and set all kinds of menus. This is washing machine Bodo, just like elevator Bodo, right there. It's only got one mode of operation. So we're going to assume that this washing machine only has a couple of buttons on there. So the button that it has is the start button. What happens when we press the start button on the washing machine? It fills up with water, right? It goes into a state where it's filling up with water. So we've got two states there that we talked about right now. State number one is idle. It's doing absolutely nothing. State number two is fill. Now we can have more than one fill state, so I'm going to call it fill one. So it fills up with water. Now when the washing machine gets full, it knows that it's full. How does it know that it's full? You're not watching it and you're pushing a button when it's full. There's a sensor in it, right? There's a full sensor. There's something that tells that washing machine it's full of water. It may be a float that floats up and down that tells that it's full, like you find in a toilet. There may be a little sensor that's mounted on the side of the tub that when water reaches it, it changes the properties on that there to where it now conducts electricity, so that that switch now closes. There's something in the washing machine. We don't care what it is at this stage of the game, but there's an input that tells it that it's full. So once it's full, then what does it do? It starts washing, right? The little machine goes to clean the clothes. So it's now in the wash state. So we could go through this whole process, which we'll do over the next couple of weeks, and we can design a washing machine that goes through the whole process. But for right now, the only thing we're trying to get across here is that a finite state machine is based on the idea that there are a finite number of states. Finite means that we can count them. So when we're looking at something like a washing machine, there's probably 10 or 12 states that's in there. Maybe more, maybe less. There's idle, there's fill, there's wash, there's drain, there's fill again, there's rinse, there's drain again, there's spin, and then there's probably go back idle. So there might be 10 states somewhere. But there's a finite number of states. An example, this is a very simple example, is a LED is on or off. Same thing, you go to a red light. There's a finite number of states. It's either red, yellow, or green. That's there. And then, of course, going from the other direction, there's red, yellow, or green. So you may have 5 or 6 states for a standard red light. North-south may be green, then it's yellow, then it's red, but while it's red, east-west is green, then it's yellow, then it's back to north-south being green. So there's a finite number of states that we move to from one state to the other. So that's what a finite state machine. And we define, as part of our design process, we're going to define what those states are. So we're looking at a system that we're going to design, and this system is based on a microcontroller like the 8051, and we're going to design the system there, and we're not even going to think about it at this point which processor we're going to use, or if we're even going to use a processor. We're going to design our system based on a number of states. So we have to look at what the final product's going to do right there. So that's what a finite state machine is. We normally declare a variable as a state variable. We're going to be writing this in C, so we're going to define a variable that's going to call current state or state right there. Now typically we will have some inputs that there, so the current can be modified by either themselves. We can have a finite state machine with no inputs. A very simple finite state machine with no inputs is a stoplight. It starts out at one state, stays in that state for so many clock cycles, goes to the next state. Stays in that state for so many clock cycles, it goes to the next state. So this is a finite state machine that has no inputs. Right there. The only input might be a timer inside that we tell it to count for 3 minutes or 30 seconds or whatever, and then when it expires, we go on to the next state. So our washing machine has multiple inputs. At least 3 inputs that I can tell you right off the bat. One is the start button. 2 is our pull sensor to tell when it's filled with water, and another one might be the empty sensor to say when it's empty, because we have to drain the water out of this here. We may have other sensors. We may have a sensor that senses how dirty the water is. There. If we rinse our clothes and the water when we drain it is filthy, we may want to do a second rinse. If it's still filthy, we may want to do a third rinse. If it's still filthy, then we probably need to get a new washing machine. That's there. So I mean, it's one of those cases that we can have additional sensors. We could have a sensor that tells how much water is still in the clothes and allows it to keep spinning until the clothes are dry enough to hang out on the line. Out there. So we can have a multiple. So again, we can have outside functions or inputs to control our finite state machine. Again, I'm repeating the same topic I did last time, but there's a reason to repeat it, is that I want you to remember this. That's there. So here's kind of one way of looking at it right here. There's multiple ways of looking at state machines. You'll hear the term Mealy-Moore finite state machines. I'm not going to go into the difference between Mealy and Moore state machines. I'm just going to talk about finite state machines in the term finite state machines. So we've got a state variable that goes into some logic. We'll see the logic and how we write this logic later on, right there. That's our current state. And then we also have, going into the same logic, some outside functions that there. So some states we will progress out of without any outside input. An example of that might be, for example, our wash cycle. Our wash cycle, the only outside input, and actually it is an outside input to our finite state machine because we set it up and we treat it as an outside variable, is an input called time expired, which is actually a variable that we're going to set up using the timer. In other words, now our washing machine will probably wash for about 20 seconds, long enough to see that it washes for some time. We won't let it wash for 20 minutes out there, because otherwise, when we do our labs, we'll be sitting there forever watching this thing. So we'll speed things up out there. But regardless, trust me, I've done the stoplight problem with it there. And I had a few students that actually used real timing on the stoplights, and they're sitting there for 10 minutes watching this thing go through one cycle. Now you speed them up in the lab, right? Yeah, you're not going to spend 45 minutes watching your washing machine wash. That's there, because we're not going to hook this up to motors and the washing machine. Our motors is going to be an LED. Our push button is going to be a wire. We're going to touch the ground right there. So we're going to be looking at there. But we have a current state comes out of our logic. That's there. That's our state variable. We have some inputs coming from the environment. When I say from the environment, it's coming from outside our code. Now there are some ones that are a little bit funny. Time expired is one. It's actually within our code, but it's external to the finite state machine section of the code. Because what we'll do is we'll set up our timer with the number of seconds we want to count down, and we'll start it right there. And we'll be going through how to set up a timer, probably next week. Actually, we'll have to set up the timer next week, so that'll be there. And it'll be a very simple function that I'll write for you in C to show you how it works up there. So another way of looking at this is a different way of looking at it. This particular graph is the graph that I would use if I'm not teaching software. And the reason I say that is that we've got combinational logic there. That's and or gates. So we can do a finite state machine using AND gates, OR gates, JK flip-flops. Usually you use JK flip-flops to determine state, next state up there. That's the hard way of doing it. Typically, if I'm going to do finite state machines in hardware, I'm going to use Verilog or VHDL or some type of hardware design language. But I don't go back to Karnoff. Does anybody know what I mean by a Karnoff map? Did you ever simplify Boolean expressions using a 4x4 matrices that you circled ones and zeros? They call that a Karnoff map, a K map. That there. Trust me, designing state machines using K maps is a pain in the neck. I don't ever want to do it that way again. I've done it that way back in the dark ages. But this kind of leads itself toward that discussion right there. And you can do finite state machines using K maps. That there in JK flip-flops. Right there. Okay. These are some benefits. I'm going to go through the slides and I'm going to go through an example right there. If you use finite state machines right, you're going to end up with a good design. This is a design tool. What separates engineering students from technology students is you're going to learn design techniques. So I'm throwing the design technique here at you. It's something we need to learn on how we're going to design something. We're going to take a process, we're going to look at it, we're going to now put it into a finite state machine, look at the steps, and then we're going to put it into hardware, our 8051 microcontroller up there. Now we're not going to hook up motors to it because we don't have a big enough lab. If we had motors that we could hook up to it in a dummy state machine or a washing machine, we could do that. We're going to go through the processes of how we would design over the next few weeks a washing machine. We'll probably take some time off from there and review some questions for the final exam as well, because there's some questions I think I need to hit that there, but I'll do that, later up there. So right now we're going to implement the application. So you have to think about what you're going to do. That we're developing a flow chart of how our process is going to flow. We're designing an embedded system. Embedded systems typically control something. So they have inputs to them. That there. They also have things that they control. They have outputs. And how are they related to each other? That's the design technique. Everything up to this point has been the tools we need, how to write the software, how to hook up a microcontroller, how to hook up the processor, how to memory. Now, how do we make this thing do something? So this is really the key of the design process right there. And this is really where, to be honest, I spend 95% of my time working in embedded systems is in this process here. The hardware is easy. I'll be real honest. The hardware is easy. It really is, because I can go and buy a board like the board that we're using for our class right there. I can put two little connectors on the bottom of it and stick it into another board that I designed the rest of my hardware around, and my microcontroller is done. I got two wires to hook up, VCC and ground. Maybe a crystal if I need high accuracy. That's there. Then everything else is connecting to the outputs and inputs. And that all comes from this discussion here. What are our inputs and our outputs to our finite state machine, and how are they related? So this is really the meat of where things are happening right here. It's right there. So and you can spend an entire career. Now, finite state machines also have one advantage. It's that they always have a home location. Return to center. They always go back to a reset mode or an idle mode. Right there. You don't leave them hanging. If you put a watchdog timer into a finite state machine, it's always going to take you back to that reset mode or that idle mode. waiting for things to happen. So they're clearing the watchdog for push button presses, periodic that there. So you go through there, and every time you go through, you just reset, hit the watchdog timer, and if you get locked up in a particular mode, that's there. So let's kind of go through a few tools that there. Okay. This is an expression in C right here. Right here. This is actually copied right out of any C manual, and this is a type of a C function here. It's called a switch right there. When you took C, did you cover the switch statement at all? So you should have seen the statement up there. It replaces a series of if-then-else's. Out there. If you use the switch case function with C with a finite state machine, the process is very straightforward, right there. Very straightforward. And I just want to kind of highlight this. I will probably get the syntax wrong because when I'm writing on a computer like this, I almost invariably leave off commas and semicolons. Those of you that write code, you're typing, you'll leave them off, let alone when you're trying to do them by hand writing out there. That's what compilers are there for. They catch those mistakes, right? Out there. We're not going to worry so much about this. But what we're looking at here is that we are going to put our state variable as our expression. So this is going to be whatever our current state is going to fit in here. Current state is going to fit there. Then we're going to list each and every possible state right there. Now this default right here will always say next state, or we set the state back to idle right there. In other words, we go back to idle. If somehow something goes wrong with our code and we end up in some state other than our list of approved states, we want to take it to idle. Something went wrong out there, and it has the way, and it does go wrong. I should say that when you look at the code, you would say that it can never happen, but trust me, it can happen. Things go wrong out there. So you always want to include the default and take that back to idle right there. So this is kind of the flow diagram of the select case right there. This is the expression, and again we're going to use our current state. We'll look at our current state. And this is if we're in state idle, for example, and this is how we determine our next state. For right now, I'm not going to worry about our outputs for each state. So we have a current state, and we look at all the current states, and we decide what is our next state going to be for each one of those. So we write our code to determine our next state right there. So here's a short little example. We're going to use this as kind of a starting point right there. I've got 3 states right here. This first one here is we're defining a type. Right there. We're defining a type. Right there. So we have a type now called myStateType is what that stands for. So we're setting up a new type called myStateType, and this type can only have 3 values. This is an enumerated type. You may or may not have had this in your C course. I would assume that you might have touched upon it. Probably didn't spend a lot of time on it. A lot of instructors that use this will use define type, and they'll list Monday, Tuesday, Wednesday, Thursday, and they call it days of the week. Or they'll list colors or whatever. In other words, these are our various types there. So we list all possible states. Right there. If it's not in that list, that state cannot happen. You have to list all of your states there. Then we declare my state T. This is our current state. This is our state variable. Right there. State, right there. I typically use current state, but you can use just state there. And this is my reset state. Right there. So what we're doing is we're setting up, we're getting to the meats and bones of how we would code this once we have this design, right there. So we have the enumerated type, right there, where we list all of our possible states, and this equals 0 is optional. You could or you may or may not put that there. It's a good idea to put that there, because typically what the compiler is going to do is it's going to actually use a byte or a char or a integer, depending on how many states you have listed. And if you set that one 0, that there, this right here equals state 1. This is the one that actually will set it up when it powers up in reset mode. The state will be in the initial idle state, right there. And I've actually done it within my code itself, where I'll put that as part of the initialization routine, where I say state is equal to idle, right there. Right there at the beginning of main, I stick in idle, just because you want to make sure when you reset, it goes to the idle state. You don't want when you walk up and power up your washing machine that it starts filling up with water, right there. Or you don't want it to be spinning. You want it, upon power up, to be sitting there in the idle mode, right there. Now you may have some cases here, and I'm getting ahead of myself, but let's say we're looking at a wash machine, and so you have a power outage while the thing's full of water. So you may want to check to see whether or not, upon power up, to see whether or not it's got water in it, and drain and turn on and go into a drain mode before you go into the idle mode. You may have what I call a power up diagnostics check right there, which normally you would have. But in this particular state, we're keeping it simple right there. So I'm just saying that it may, when you get into a real project, things are not always that simple, because you power up a washing machine, the electricity went out while it was in the middle of a wash cycle, it's full of water, what do you do? You have to clear the water out and do something with it there. So, but for right now, we're going to assume that that can't happen. Now we can do it a little bit by, in the idle mode, we can open the drain valve, for example, and that may solve some of that right there. So, okay. Now, for every possible state here, in this case we have 3 states, we list the states on the left-hand side here. This is our switch, and this is our state variable. This is just foo, that's just for whatever. This is just calling this to determine the next state within our program here. And we look at right here, and we determine what our next state is. So this is here. What we're going to see here is that we're going to have here, for example, in this particular case, we have an if then else. We look at input. If input is true, then we go to state 3. Else, we go back to state 1. So we have, this is a 3-state machine. If input is true, it goes here. If it were here, and if input is false, we go back to here. If it's true, we go to here. And in state 3, we don't know what we do because the code hasn't been written yet for state 3. So, but this is where we define this. So now I'm going to go back to our washing machine, and I'm going to start, first off, I'm going to start with the design process on our washing machine. That there. And I'm going to spend the rest of the next probably 45 minutes going through our washing machine and go as far as we can. I will not write all the code for our washing machine from scratch, that there. But let's just jump back here and let me disregard. Let's go through our washing machine here. Let's go ahead and bring up OneNote. Right here. And let's look at right here. First off, let's just come up with a list of states. And I'm going to write these in the order in which I would write these. Now, if I leave one off, and you guys see that I left one off, please raise your hand and yell at me, okay? And don't throw anything across the room, but at least raise your hand. You know, I got my glasses off, I can't see your faces, but I can see hands going up here. So we're going to start off with, our first state is idle, right there. So when we first power this thing, we go to idle. Where do we go to after idle? You push the start button, you go to fill. You fill it up with water. And I'm going to put a 1 here. And the reason I put a 1 here is these states need to be unique. And I'm going to fill this thing up at least twice. That there. So you'll see me put a 1 there because in this particular case, I'm going to fill it before the wash cycle, and I'm going to fill it again before the rinse cycle. And let me just kind of put over here is our major states: idle, wash, drain, spin dry. And I'm doing a spin drain here. Spin dry, and then back to, you know, this is the general flow of a wash machine, right? You know, there may be two drain, two rinse, and actually, I meant to put rinse here, right there. Now, the wash has 3 parts to it. It has a fill, it has the actual wash, agitate, and then it has a drain to it, right? So there's 3 substates to wash. So as you look at my washing machine, I've got 4 major states, but each of these major states have substates to it. And that's not unusual that there. So in the wash cycle, I'm going to fill it, and then I'm going to do the actual wash, and I'm going to put an AG here for agitate. That's what the motor does, it agitates it. I don't know what, is there a Malay term that's more accurate, but we call it the agitate mode, where it's the motor goes back and forth. That there. So, what's that? Agitate is the term. So it's going to be in the agitate, and then it's going to drain. So it goes through these, and I'm going to put a 1 here. So it goes through these 3 states, just to wash the clothes. At the end of these 3 states, what you've got is a clunk of clothes at the bottom of the washing machine that are filled with water, right? They're completely filled with water there. And the water is nasty, soapy, dirty water, right? So chances are the next thing we want to do is get all that dirty, nasty water out of there. So we need to go through a spin cycle just to get that water out. So we've drained this. So then we're going to go through and I'm going to call it spin 1, right there. And we're just going to spin this thing for a few minutes. And the whole idea of the spin cycle is just to get this nasty water out of that there. So once we're done spinning that there, we're ready to start our rinse cycle. So the first thing we need to do as part of our rinse cycle is we need to fill 2. We need to fill it up again. Right? Now we're filling it up with clean water. Then we're going to do a rinse. And I'm going to put an AG there and agitate that. We're going to sit there and we're going to take our motor, go back and forth, and you know, basically take our clothes and run it, you know, move it in and out of this clean water. And we're going to do that for so many seconds, hours, minutes, however long it takes. And then we're going to drain it again. Drain 2. We drain it again. Now, our next step is a spin dry, so we don't need to do another spin cycle before we go into the spin dry. Then we just go through a major spin cycle, or spin dry, right there. And then after our spin dry, we go back to fill, or excuse me, idle. So that's our basic flow of how our wash machine is going to work. I can go through any process up there and come up with a similar flow diagram. Now, some processes have multiple branches. If we look at a microwave oven, I have a grilling button, a convection oven, that there, and it will go to different branches. That there. I'm just right now I'm using a simple one that's very linear. When I say linear, it goes in a straight line. It doesn't backtrack. You know, we have some that will backtrack right there. So this is all of our states right here. So if we're going to write our code, we could go ahead and write this. You know, I'm seeing 1, 2, 3, 4, 5, 6, 7, 8. I've got 9 states that I'm operating in right there. Right there. So what we're going to do there is we go through our 9 states right there. We're going to basically start our process here, right there. And let me just kind of go through this step by step, and I'm going to just sit here and write some code here. The first thing we need to do is I'm going to back up here. Actually, no. Right here. Right there. These are our 9 states. Let me go back to our PowerPoint. And look here, our first step is we have to write our enumeration right there. Right there. We have to define our type right here. So this is the first thing we're going to do right there. Right there. Is that there? So let's just go ahead and stick that up there. So we're just going to do a type def right there. And again, I can't remember syntax right there, enumerated, so it's type enumerated. Right there, and bracket right there. And we list our various states with commas in between them there. And normally you capitalize these. So our first state is idle, and that's equal to 0, comma. Our next state was fill 1, comma. Then wash AG, right there. Drain 1, comma, and that should be a comma there, not a semicolon. And then spin 1, comma, fill 2, comma, rinse AG, comma, drain 2, comma, spin dry. Close bracket right there. Right there, and then my state. Okay, I forgot the. And my state type semicolon right there. So we've defined that, and there should be 9 of those. We counted. Is there 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've listed all of our 9 states right there. Right there. Now, on a side note, I'm going to just kind of list the inputs we're going to have. And I'm just going to do that as a separate thing up there, simply because we need to know that. I'm not going to worry about outputs at this time. Outputs we'll treat totally separate. We'll set our outputs up later, right there. Although there is going to be one output that I'm going to call, and I'm going to call it TE, which I'm going to, it's an input output, and it's for my timer, right there. Right there. So I'm going to list this here as TE, and that's my time expired, that there. And we're going to set that to, if we say TE is equal to 0, right there, that means that we've cleared it, and then we're going to have num sec equal to whatever. That's part of our starting our next state right there. And then our start timer is a function call right there. And we could actually put the number of seconds in there. So actually we can just do it all in one spot there. So I'm going to declare a function right here. Later on we'll talk about, it's going to call it start timer, and I'm going to pass it the number of seconds I want it to count down, and it's got a variable attached here called TE that we set as 0 before we call it, and then when the timer expires it's going to go to 1. We're going to use that for counting down right there. So I'm right there, and that's a standard way of doing time delays right there. So I've got this variable, let me make sure everyone's clear on this. It's called TE, it's for time expired. Before I start any kind of timer, I set that to 0, and then I call this function, and we'll write this function later, much later, right there, not today. We'll write this function called start timer, where we tell it that we want to count down for 30 seconds, and it's going to load into a variable the number of seconds, and it's going to start one of our timers, and then every second it's going to subtract 1, and when that equals 0, it's going to flag an interrupt that's going to set TE. So TE will actually be set in an interrupt right there. So we're going to set it to 0, but then our interrupt's going to set it to 1 whenever our timer expires. So every click we're going to subtract 1, we're going to check the status of TE, and then we're going to, you know, we'll just keep on moving from that there. So when we call this function right there, so, and again, I haven't wrote that yet for this particular processor, but it's fairly easy to write. Okay, so then the next thing we need to do is we have all our states. Well, we need to see our inputs. So our inputs are very simple. We've already talked about them. One input is start, right there. And that's our push button on the front to start the machine. Right there. So that's our push button to start the machine. Another input is full, and that's a sensor that is high whenever the washing machine is to the preset level. Now, I don't expect the guys to know this, but some of the ladies know that there are washing machines where you can set a knob to say whether it's a small load or a large load, right? Right there. I wouldn't get away with this in the U.S. because I couldn't pick on the guys like that, because some guy who knows how to do laundry would say that I was being sexist and saying that guys don't know how to do laundry. But here I can get away with it, right? Most of you guys don't do much laundry, do you? You say you do? You do? Okay. Then I should make that assumption. I know that all my wife's nieces' husbands have never touched the washing machine, as far as I can tell. So maybe when they were single, they knew how to do laundry, but once they got married, they never saw where they don't even know where it's at. It's somewhere outside. All they do is put the laundry in the basket. Although I have to be honest, that's what I do for the most part now too. But I do know where the washing machine is because I had to hook it up. You know, I had to read the manual and show my wife how to use it. That's there. So, but regardless, there's a button that, you know, there's a sensor that's going to say when the washing machine is full. Now, some washing machines have a selector where you can say whether it's a small load or a large load or a medium load we're going to ignore that for our machine here. It only has one sensor that says the machine is full. Actually, it's the same way if you're using a machine with the sensor that just adjusts the sensitivity or selects which sensor it's going to use in the tub right there. So, but right now we're just going to use one sensor that says that the sensor is full. We have another sensor that says it's empty right there. We have another sensor that says that it's empty there. And that one we assume that there's only one sensor right there. I think those are the only sensors we have that we need to deal with right now. There are other sensors that would be added on a real washing machine, such as the door safety switch. There would be outputs that we would add, such as a door lock. You know, if you look at a top-loading machine, at least the ones that I've seen in the U.S. and Europe, that when the thing's spinning, you can't open the door. It's got a lock on it. You have to hit the stop button and wait for the thing to stop spinning, and then you can open the door. Why? Probably because some idiot opened the door and stuck their arm in there and ripped it off. That's there. That's the reason they put these things, interlocks in that there. But regardless, but for right now, we've only got that there. So let's now look at our you see our select case function right there, which is right here. As we look at this right here, our switch case statement, and I'm just going to worry about the switch state that there. Actually, I need to do one other thing here is I also need to say my state T, and I'm going to call it C state right there, and equal idle right there. That's somewhere in the beginning of my code within my main function. This actually has to be, this enumerated type actually has to be outside your code up at the top where you define all your, where your includes and everything else. But this line here is typically within main. Right there is where you would stick that there. So there are two totally different parts of the code. You don't define the type within the function main, you define it outside main. Out there. In the same place where you define all your equates for your ports and all your addresses and all those things up there. So this goes within main right there. So elsewhere within main, we have our switch right there. And our switch is using current state right there. Right there. So our switch statement, we're going to look at the current state right there. And I keep looking back at the sample simply because I put that there because I wanted to see whether I put the squiggly brackets there. As I said, I don't guarantee my syntax is correct, but let's try to cheat and get it as correct as possible. So our first case is state. Our first state is idle. So when we're in idle, what do we want to happen? Well, let's just keep life simple. We have a start button, right? Right there. So we're going to simply, and as I cheat back and forth, actually if I had two monitors, I would, right there, state, and we got to put the colon here. That's why I keep cheating to go back there to catch her. So we simply say if start. Now you can put the equal 1 there if you want, or you can leave the equal 1 off. The example I had left it off. The assumption is this is a single bit input that we set equal to port 1.1 or 1.0. So start is a input that's been defined elsewhere at the beginning of our code, same place where we put our type definition. If start is equal 1, then our next state is going to be fill, right? So our next state equal fill 1, right there. If anything else is pressed, we don't care, right? That there. Now we could, for example, set up another state where we do a drain and things like that, but I want to keep life simple. But in this particular case, we're just going to do a break right here, right there. So when we look at the idle mode, we can only go one place, and that's to the fill 1, right there. If the start button hasn't been pressed, then we just simply stay in idle. We don't change that there. There are some programmers, and there's nothing wrong with it, that will stick in here an else current state equal idle. Right there. They would stick that in before the semicolon there. There's nothing wrong with that. It's not needed if you're doing in C. If you're working in something like VHDL or Verilog, then you might need that. That's why you'll see some programmers will stick that in there. Like myself, I would probably stick that in there because I've designed finite state machines with multiple tools. Some tools require you stick it in there, some don't require it. It doesn't hurt to stick it in there. So I'm just saying you could put the else in there. It does make your code a little bit larger. That's there. So that's there, depending on the compiler. So that's our case that there. And I'm going to just kind of go through a couple more of these that there. I've been talking about a little, not quite an hour here. Let's just do a couple more of these here that there. The next one is, once we're in the fill, and I'm going to do this, will it confuse people if I do this page by page? Hopefully not, that there, because otherwise it gets very full. So our next one is a case fill 1, right there. So if we're in fill 1, we can only go one place, and that's to wash, agitate, right? And we don't do that until the full command is that there. So this is very simple, similar. If full current state is equal to wash, this should be AG, right there. And that's it. That's the only thing. That's the only thing we do. From we're filling this thing up, and we don't do anything until it's full, right? And once it's full, we go into the wash thing there. Now, our next case, and this is a little bit more complicated. Right here, if next case wash AG, this is a little bit more complicated because in this particular case we want to start a timer. Not there. So actually what I find easiest to do is to break the wash agitate into 2 states. One to start the timer and one for the wait. So I'm going to do that here. I'm going to generate another. That means that I've got to go back to here, and I have to add another state here, another state here, another state here, and another state there. So I have to add 4 more states. That there, a wait state. That there. So I, now I've already caught myself with I made a mistake. That there, but that's okay. I'm still early in the process. I can add those 4 states. That there. There's another way. It's a little tricky where you do the delay right here, but then you tie up the processor because we may want to do other things. Right there. So I'm going to go ahead and at this point, I'm going to start the timer here, and then I'm going to generate the next state, knowing that there. So the first thing I want to do here is I want to say TE is equal to 0, right there. That there. And TE is the one that starts, is our timer, that there. And then I'm going to call start timer. And I'm going to pass it 20 for just sake of argument right there. And then I'm going to set current state equal wash and I'm going to give it a W for wait right there. In other words, this state right here is the state in which it's actually doing the washing. What we're actually doing here is this state here is actually starting the timer, is what it's doing right there. So our next state right there is our next state case wash W right there. Now we're waiting for this thing to finish washing. So then we just simply say if TE right there. In other words, TE is a variable. I set it on the previous page equal to 0 right there before I went into the state, but then I call it start timer, and TE is a variable that I should point out, a little note here, TE has to be a global variable right there. When you took C, did they explain global and local variables? No. Okay. Let me take a minute to talk about this, and then we'll finish this up here. A local variable is one that's defined within main. It only exists within main. So if I go to an interrupt service routine, or go to another function like start timer or whatever, TE, that, a variable that's defined within main, if it's defined within main, doesn't exist. I can't change it. I can't do anything with it. If I define it at the beginning of the code, the same place where I define, the type definition, I include that they're outside any function. So when we look at C, we've got this area up here where we have our includes right there. We have our type definitions, we have our equates, and we could also have our global variable definitions right there. And then we have main right there. There's main, and then we have what other functions we have. These are all within functions. Within each of these functions, I can declare a variable right there. I can declare variables. Those variables are local within only that function, and they can't be seen outside that function. They're local variables. Variables that are defined outside of any function are called global variables. They can be seen by all functions within the code. Good programming techniques, and if you take programming from a true programmer that harps on the programming, they will flunk you in a heartbeat for using global variables. They hate global variables. They cannot use global variables. All variables have to be local and pass back and forth between functions. That there. You have to pass everything. You cannot declare a variable outside of a function. That there. I agree with these people. They're great programmers. I've worked with them. They know programming better than I can even think about knowing programming. These guys are great programmers. I've had guys that taught courses for me when I was department chair on C programming that were like this. Exception. And they don't like to talk about this exception because they're programmers. They're not embedded process or project designers. They don't work with microcontrollers. They work with microprocessors. They work with desktop computers. Exception is when you've got a variable that has to be changed in an interrupt. And the reason is because you can't pass a variable to an interrupt service routine. It has to be a global variable. We're going to be setting up timer here using one of the timers. And we're going to pass start timer. We're going to set it up to use timer 2, 3, one of our timers. And we're going to set up a variable within timer that's going to count down how many seconds it's going to count down. And it's going to, every so often, it's going to get tagged where it's going to subtract 1 from that there. So anything that's used that's going to be flagged within an interrupt service routine has to be global right there. So when we look at this right here, we need to realize that timer has to be global there. Now I could call a function right here, and I may very well change this where I say check timer right there, and I pass a TE right there, where that will go out and check the timer. Well, I won't even pass a TE. I would just that there. And what that will do is it will actually check the timer and update TE if need be. But TE should be updated automatically by our interrupt service routine right there. So what happens here is that TE is a global variable in our interrupt service routine. When we called it on our previous page, it's going to start the timer. It's going to set it. We set it low. It starts the timer, and when we're done counting, after 20 seconds or whatever we pass that to it, it's going to take TE high. So within our wait state, we wait for TE to go high. When TE goes high, then our next state is equal to drain 1, else our current state is equal to wash. We continue to wait for the wash W right there. And that's it right there. So that's all that happens, but a lot has to happen in the background here that we haven't talked about, is that we have to have this timer set up right there. Because we're now waiting for this out there. So this timer, this variable TE has to be handled within our interrupt service routine right there. So we want this thing to generate up there, and that's probably where we're going to probably start when we start looking at our project, is coming up with a way of developing this timer right there. I have not wrote this for your processor right there. So we're going to do this together as a group. We'll sit there and we'll look at how we would pass this a number of seconds and then have it light an LED after that many seconds right there. Then we'll pass it something else and see if we can change that there. So we're going to come up with this function here right there, and we'll talk about this a little bit more tomorrow morning on how we develop this function called start timer that's going to start the timer, and then we're going to write the interrupt service routine that's going to read the number of seconds that we set it to on the start timer and decrement that. And we may have to say, we could use the same timer we had that did 500 milliseconds. We just we just pass it twice the number of seconds, and we subtract off from it right there. So we can look at the delay function that I went through the other day in class. We could probably use that as our starting point right there, because that particular one there will flag an interrupt every half a second, right? Right there, that did half a second. So every time it did an interrupt, instead of flipping an LED on or off, we subtract 1 from a count right there. And then when that count equals 0, then we set TE equal to 1 right there. So it's probably a fairly easy thing to do right there. And we'll do that tomorrow. I think I'm gonna kind of wrap up here. Is this making sense where we're going with this here? Obviously, this is a big project. This is more than an hour and a half. Right there. Let me stop our recording here, and I get to go down.